Happy Tuesday, gals and guys. I hope everyone is doing well and that your week is going okay so far. Today, I want to finish off matrices with you guys, and particularly the multiplying of them. So, from yesterday, if you recall, I started to show you how we actually perform matrix multiplication through looking at linear functions that have different variables for either their input or the output. And in particular, the example that I left you left you with yesterday was this example here of this function f that had two variables x and y as their input, and then the output was this single variable expression here of 3x plus 2y. And based upon what we have here, because of the relationship of our function, I claim that we can represent the function f with this matrix that is 3, 2, a 1 by 2 matrix because there's one row and two columns. And then because of, if we looked at the specific example when x and y were both 1, the overall output was 5. I showed you that if we took this matrix of 3, 2 and multiplied it by this matrix 1, 1, which is a 2 by 1 matrix because there are two rows and one column, the way that we do this multiplication out is this 3 gets multiplied to this 1, this 2 gets multiplied to this 1 here, and then after multiplying those expressions out, we add them up to get the end result of multiplying these two matrices together. Now, before we look at our very first example today, I just want to remind you guys about our parametric equations. Right, this here would be an example of a set of parametric equations where t is our parameter, and remember that is the input, that's the independent variable, that is like the input to the set of parametric equations. And whereas we have one variable expression to represent the input, with parametric equations, the output are the variables x and y. We're getting two variables as the output to this set of parametric equations. And so technically, especially when we're dealing with these linear expressions, the number of variables that we use for our input and our output can vary from one example to another. So let's look at our first example for today. So for the first example, I want to start off with a function that will have just one variable as its input into our function f. So I'll just use the variable x as the variable, single variable that's being plugged into function f. And then the output here is actually going to be two variables. There'll be two outputs for this particular function f. And so I'm just going to make up particular output values. The first output value I'll just make up will be 3x, 3 times this x. And the second output value, I'll just make that to be 5 times the variable x. Now, the additional thing I want to do with this example here is I don't want to just have one particular function. I want to have f be composed with the function g. And now g is going to take these two variable expressions as its input, and it's going to spit out just one output. And the variable expression that will perhaps represent the output of the function g, I'm just going to make up an expression, and in particular, I'll just make up the expression of 4x minus 2y. Now, you may say, well, where is this value y coming from? Well, I have to give different variables to represent the two different inputs that are coming into the function g. So this x here is going to be associated with the first input into the function g, and this y variable here will represent the second input into this function g. So now with these expressions to represent the variable outputs to the functions g and f respectively, let's perhaps look at a specific numerical value for x and see what the overall output is when we plug 1 into the functions f and g respectively in those composed functions. So when we take 1 and first plug it into the function f with x equal to 1, the two outputs will be, well, the first output would be 3 times 1, and the second output would be 5 times 1. And we can simplify that down to just being 3 and 5. But then from there, we would plug these two input values into our function g. And when we would do that, we would first get 4 times the first input value of 3 minus 2 times the second input value of 5. And we could simplify that down. If we did this here, we would end with end up with 4 times 3, which is 12, minus 2 times 5, which would end up being value of 2. And so whereas we compose the two functions f and g with a specific numerical value for x, what I would like to do next is I would like to perhaps just take the variable x and run that through the two functions here to try to come up with a variable expression to represent what is the rule for composing the functions f and g. So again, start with the variable x. If we plug that into our function f, we will end up with the outputs of 3x and 5x, which we would then subsequently plug into our function g. And the function g's output is this 4x minus 2y expression, variable expression. So using these values, these actual values of 3x and 5x now to plug in to the function g and end up with this one variable expression output, we would get 4 times the value of the first input of 3x, and then we would subtract from that 2, subtract from that 2 times the second input value to the function g of 5x. And now, if we simplify this out, hopefully you would agree that both these expressions here are going to be like terms. They're both going to be expressions in terms of the variable x, but I actually, because they both have the variable x in it, I want to factor that x out first from both of these terms and then write what we have left over. So if we factor out x from this first term here, we would end up with 4 times 3. And then if we factor out x from the second term here, we would be left with negative 2 times 5. And if you look at what's inside this parentheses here, hopefully you recognize that as being exactly the same thing as what we had over here technically. And so, okay, if we simplify this, then we should get, once again, 12 minus 10, which just leaves us with 2x. And so technically 2x would be the expression that would represent the composition of our functions f and g respectively. But I claim that this coefficient of 2, which is equivalent to this 4 times 3 minus 2 times 5, could have been found by setting up matrices for both of the outputs of f and g respectively and performing this matrix multiplication. And so technically the matrix that we can set up for the output of our function f could be represented by this matrix here of 3 and 5. So we would have here this 2 by 1 matrix because there are 2 rows and 1 column in this matrix here. And the matrix that we can set up to represent the output for the function g would be this matrix of 4, negative 2, where this would be a 1 by 2 matrix because we have 1 row and 2 columns here. And if we then take this first matrix of 4, negative 2, and then multiply that by the second matrix here of 3, 5, and follow the way that things are being worked out here, right? We multiplying these matrices out, we would take 4 and multiply that by 3. So again, we take this first value in this first row here, 4, and multiply it to the first value in this first column here in the second matrix here. So we have 4 times 3. And then we would then multiply negative 2 times 5. So this negative 2 comes from the second value in the first row here, and the 5 comes from the second value in this first column here. So we'd have negative 2 times 5. Right? And then this matrix here just ends up being the matrix with the value of 2. And so once again, hopefully you start to see the process to how we actually perform this matrix multiplication. Okay, so now for the second example, I'm going to once again compose two different functions f and g. For the function f, however, we're going to start off in this example, the function g having two variable inputs, and I'm going to use the variables x and y to represent the inputs of the function f. And the output of our function f is actually, there's going to be 3 outputs. So there'll be 3 variable expressions to represent the output of our function f. And those outputs, again, I'm just making these up. So the first output I'm going to represent by the expression, the variable expression 2x plus 5y. the second output of our function f will be the variable expression x plus y, and the last output of our function f will be represented by the variable expression 6x minus 3y. So now we're going to take these three expressions, these three variable expressions, and we'll plug them into the function g, and the output of the function g is actually going to be just one variable expression. And the variable expression to represent the output of our function g, and again I'm just making this up, will be the expression 3x plus 4y minus 2z. And again, I need three different variables here because of the fact that there are three inputs into the function g, and this x represents the first input, this y represents the second input, and this z just represents the last input into the function g. So this is the outputs for the functions f and g respectively. And what I'm going to do in this example here is I'm going to go right towards trying to get an overall expression to represent the composition of our functions f and g. So starting with the variables x and y, right, we know that when we plug them into the function f, these are the three variable expressions that we get from that particular output. But now from here, I'm going to take these three particular variable expressions, and I'm going to plug them in respectively into where we see these variables here as the output of our function g. So that will mean that we'll have 3 times the first input value, which is represented by this 2x plus 5y expression. And then we'd have next plus 4 times y, which represents the second input into our function g. So we'd have here 4 times this x plus y. And then last we'd have minus 2 times z, which is the last input value into our function g. And so this here, it's a lot, but all this here will represent the one single output that we get from our function g. And now I want to simplify this down a bit, and we could distribute in each of the values 3, 4, negative 2 into respective parentheses and then combine like terms. And hopefully you'd agree that we would have terms in terms of both x and y. But what I'm going to do is I'm going to take and group together all the x terms and factor out the x from those like terms there, and then do the same thing with all our y terms, factor out the y from all the common y terms. And so I'm going to do that, and I'm going to go quickly towards getting what those actual terms would be. So from the first parentheses, the x term there would have a coefficient of 3 times 2. So I'm just going to write out that 3 times 2. And again, I factored out the x already. From the second parentheses here, the x term here would have coefficient of 4 times 1. So we have plus 4 times 1. And again, I factor out the x already. And then the x term from the last set of parentheses would have coefficient of negative 2 times 6. Negative 2 times 6. And so we could, combine all this together here. And I claim that if we were to do that here, we would get negative 2x. Now for the y terms, the coefficient of the y term from the first parentheses would have value of 3 times 5. And again, I've already factored out the y term here. The coefficient of y from the second parentheses would be 4 times 1. And the coefficient of y from the last set of parentheses here would be this negative 2 times negative 3. And if we were to calculate what this actually equals out, I claim that we would get a value of 25 as the coefficient of our y term. And so negative 2x plus 25y would represent the expression that represents the rule of the composition of our functions f and g. And whereas I went through the process that I did here to find that overall rule, I claim that we could have found this end result by multiplying the matrices that represents the outputs of these two functions. So the matrix that we could use to represent the output of the function g, I claim would be the matrix 3, 4, negative 2, right? This would be a 1 by 3 matrix, one row with 3 columns. And the matrix that we could use to represent the output of the function f would be 2, 5, 1, 1, and 6, negative 3. And this matrix here, right, would be a 3 by 2 matrix because there are 3 rows and 2 columns. And again, I claim if we multiply these two matrices together, we would get the same result here. So the way that we would multiply these matrices out would be the same as what you're essentially seeing as technically the coefficients of the values of the variables for x and y here. And in particular, right, if we look at this here, the first value that we have as as part of the coefficient for the value of x would be this 3 times 2, which I claim would be obtained by taking this first value in this first matrix here of 3 and multiplying it to the first value in this first column here of 2, right? And so if we actually start that multiplication out, we'd have, again, 3 times 2. And then from there, the next value that we have here is 4 times 1, which we get by the second value in this row here, multiplied by the second value in this first column here. So we'd have then from there plus 4 times 1, again, 4 times this one here. And then from there, we take this last value in this first row of -2, and we multiply it to the last value in this first column here of 6. So again, it's -2 times that 6. And so, again, doing that multiplication out and then adding those values up, we would end up with a value of just -2. But then for the second value here, that is obtained by multiplying out all these values here to our coefficient of y, which I claim is obtained by going back to this row here and doing basically the same process to the values in this second column of this matrix here, right? Because we have here 3 times 5, which is, again, this first value of 3 here in this matrix here times the first value in this second column here of 5. So again, 3 times that 5. So we have 3 times 5. And then from there, the next value is 4 times 1, which is obtained by taking this value of 4, which is the second value in this first matrix here, times the second value in this second column here of 1. So plus 4 times 1. And then lastly, I claim that this last value here, this -2 times -3, is obtained by taking this value -2 and multiplying it to the last value in the second column here of -3. So add to this here, -2 times -3. And again, if we add that all up there, we get the value of 25. And so this matrix here is the end result of multiplying these two matrices together here. And this matrix here, this -2, 25, right, is the same value as the coefficients of x and y that we saw as the rule for the composition of functions f and g. Now, this process of multiplying matrices, again, you whatever row you have here, you take that and you start off with the first column in your second matrix here, and you just multiply respectively the values in this row here to the respective values in the column here, and then you add them up. And then if you have more columns like we did here, you just continue that process. And so if you had even more columns here, you would just continue with multiplying this row to each respective column to get, further values in the end result of the multiplication of the two matrices together. Now, it is possible for this matrix here to have more rows, and if that were the case, after we were done taking this row, multiplying to each column in this matrix here, we would then go to the next row in this matrix and then do the same procedure of taking that row and multiplying respectively to each column in the second matrix. Now, the other thing I'll say is that matrix multiplication can't be just done in any two matrices. There are certain conditions that have to be met amongst your two matrices, and this has to do with the dimensions of each respective matrix. So this first matrix, again, I said was a 1 by 3 matrix because there's one row and 3 columns. The dimensions of the second matrix, I said, was a 3 by 2 matrix, right, because there are 3 rows and 2 columns. Now, in order to be able to multiply any two matrices together, I claim that the number of columns in the first matrix has to match the number of rows in the second one. If these two do not match up, you cannot multiply out those two matrices. Furthermore, when you are able to actually multiply two matrices out, I claim that you will know what the end result is, because I claim that the number of rows in the first matrix and the number of columns in the second matrix will actually be the end resultant dimensions of your multiplying of those two matrices together. Because this matrix here, if you look at it, right, this is a 1 by 2 matrix, which again you would know before you actually multiplied out those two matrices. This is essentially how we in particular multiply matrices together. I know that's a little bit of a weird process, and that's why I'm posting a second video today, just to go through an actual example, just multiplying out two matrices. But I hope that this video in particular helped illustrate further how we actually multiply these matrices out, and not only that, just why in particular we do the matrix multiplication in this manner. So that's it for today, or in this video I should say, and I will post one more video tomorrow just to kind of wrap things up a little bit. So I hope that you guys enjoy the rest of your day today, and as always, please take care, stay safe, and I will talk to you soon.